Okay, so welcome to video number 4 for bmb540. In the previous video, you have looked at how mechanical work is calculated, and we typically use an example of a gas confined with a piston right here. Um, the work in such a system is the area under the pressure volume curve. When you are expanding the gas reversibly, then you make sure that the external pressure is just a little bit higher than the internal pressure. So in fact, in this pressure volume curve, you're plotting P external, which is almost always equal to internal. The internal pressure must be a little bit higher than the external pressure so that the piston can expand. This image is taken from Korean, and here you can see that for a slight increase in volume, there is a slight change in pressure, and that is uh, the infinitesimal amount of work done. And for the entire reversible process, the work done is the area under this large curve. If the work is done against a sudden irreversible expansion, then the area under the curve is much smaller and you get lesser work done. The difference between heat and work in one way is that um, heat is energy which is transferred completely randomly, as in this case, while work is energy that is transferred in a certain direction, such as in the expansion of this gas along this direction here. So here is a question. If work is being performed at constant temperature by the system, then what else is changing in the system? Is it internal energy, W, or Q? Does the internal energy decrease? Does the internal energy increase? Does heat leave the system or does heat enter the system? And the answer to this is in this image here. Um, if the work is being done isothermally, so look at the image on the right hand side. If the work is being done isothermally, then there is no change in the internal energy, which depends on temperature for an ideal gas, and therefore heat flows into the system. And you can calculate this from the first law, which says delta U equals Q plus W. Since delta U is equal to 0, Q must be equal to minus W. The system is doing work, so W is negative. That means Q is positive, which means heat is flowing into the system. Here is another example, a biological example of expansion work. Whenever we breathe, we do a lot of work when we expire or when we let out a, a breath. Let us try to calculate how much work we do when we breathe. So here is an example that we will do. Calculate the work done in exhaling half a liter of air against atmospheric pressure. And we will compare this to the work done when we lift a heavy book of about 7 kilos from the ground to the table. So here is the calculation. The work done by exhalation is equal to the external pressure multiplied by the change in volume and a negative sign. And if you plug in the numbers, you get a value of about 51 joules. And since we are doing work, the answer is negative. So every time you let out or you exhale about half a liter of air, you do 51 joules of work. If you take a heavy book of 7 kilos, so that it's probably 2 Korean or 3 Korean books, then the work done is mass multiplied by the gravitational constant multiplied by the height. And if you plug in the numbers, you get about 52 joules. So every time you breathe out half a liter of air, you're doing an amount of work which is equivalent to lifting a heavy book from the ground to the table. So the breathing requires a lot of energy. We'll come back to this later, the work required in breathing, a bit later during the course. Here is another example of work calculation. We have argon gas which has a certain mass and occupies a certain volume at a certain temperature. And then we want to calculate the work. If the work is isothermal against a constant external pressure and the volume increases a little bit, or if the same expansion occurs reversibly. Normally, I would ask you to do it in class, but this is not possible here, so let's just calculate the numbers. Work is equal against a constant external pressure is equal to the external pressure multiplied by the change in volume. And the problem says volume has increased by 2.5 decimeter cubed. So delta V is 2.5 into 10 to the power minus 3 metric cube multiplied by the external pressure with a negative sign. So this is about 20 joules. The work done by the gas is minus 20 joules. If the same expansion were to occur reversibly, then this would be the expression where you would put in the numbers minus number of moles, gas constant, temperature, log final volume by initial volume. And since the volume has increased by 2.5, the final volume is 18.5 plus 2.5. The initial volume is 18.5 and the work done is minus 53 joules. So for the same amount of expansion, reversible work is much higher than non-reversible work against a constant external pressure. We have talked about enthalpy and heat in another video. Heat is typically calculated most easily by calculating work and internal energy differences. But if neither of these are directly measurable, one can use calorimetry to do this, where one calculates a change in temperature. We will come across calorimetry again during one of the computational laboratories. I have also talked a little bit about heat transfer at constant volume and heat transfer at constant pressure. It is worth repeating that the internal energy is the heat transferred at constant volume, while the enthalpy is the heat transferred at constant pressure. Here is another question. We have an ideal gas that needs to be heated by about 10 Kelvin. If you want to use the minimum amount of energy or minimum amount of fuel, would you rather heat at constant volume or at constant pressure? And the answer is you would rather heat at constant volume, because when you heat at a constant pressure, the system expands, and when it expands, the system is doing work. So some of the energy that you supply to the system is spent in doing work. If, however, you keep the volume constant, the pressure keeps changing, but all the heat that you supply goes into changing the internal energy of the gas and increasing the temperature of the gas. I'm sorry, on the right hand side, the pressure is not constant. I'm sorry, the pressure is constant, but the volume is not constant. So the right hand side is heating at constant pressure, while the left hand side is heating at constant volume. Another question about heat capacity. If the heat capacity of water is higher than the heat capacity of acetone, which one would you use to cool nuclear reactors, for example? And the answer is water, because then you would have to use a lesser amount of water, because 1 kilogram of water will absorb a larger amount of heat than 1 kilogram of acetone. A couple of examples on internal energy and enthalpy calculation. You can read these problems. They are taken from Atkins. I will give you a couple of minutes to read the problems, and then we will go further. Good. So we can continue. So in the first example, heat is being supplied at constant pressure. So one must use the heat capacity at constant pressure. So the heat supplied is equal to the number of moles, multiplied by the molar heat capacity at constant pressure multiplied by the change in temperature. And if you plug in the numbers, the heat capacity at constant pressure, the molar heat capacity at constant pressure is 37.06 joules per Kelvin per mole. And from this, you can also calculate the heat capacity at constant volume, the molar heat capacity at constant volume. The second question says that we need to use the information we use here, found here, to calculate the change in enthalpy and the change in internal energy when carbon dioxide is heated from 15 degrees to 37 degrees. So this is essentially the amount of work that we are doing in cold weather um, when we inhale something. So if we inhale cold oxygen, we need to heat this oxygen, and this estimates for you how much energy we spend in doing this. So when carbon dioxide is being heated from 15 to body temperature, the delta T is about 22. The change in internal energy is the number of moles multiplied by the molar heat capacity at constant volume multiplied by the change in temperature. If you divide both sides by the number of moles, then on the left hand side we have the molar internal energy. So that's the internal energy divided by the number of moles. And this is about 632 joules per mole. And similarly, you can get the molar enthalpy change, which is CPM, molar heat capacity at constant volume multiplied by a change in temperature, and this is a bit higher. We haven't talked much about how heat capacities change with temperature, but for an ideal gas, for a reasonable range of temperatures, the heat capacity is more or less constant with temperature. So here in this plot, you have heat capacity at constant volume on the y-axis and temperature on the x-axis. For a complex system such as a protein, this is a bit different. So if you look at the curve for the protein, up to a certain point, the heat capacity remains more or less constant with temperature, after which it suddenly increases and then decreases. It is increasing at a point where a phase transition is occurring, where the protein is getting unfolded. And you see similar heat capacity curves when you change the phase of a lipid membrane from the gel phase to the liquid phase. We will learn more about these heat capacity versus temperature curves and phase transitions in a later lecture and also in your laboratory.